up until this point, we have dealt with how reaction rates change as a function of rate factors. The rate factors we've identified by the little acronym can't see. Concentration effects, area, surface area, nature, temperature, and energy effects, and catalyst. We haven't said much about catalyst, and I'll emphasize this after this section. It takes a minute. But we've covered everything in here that can be covered at this level except the temperature energy issue. To understand this temperature energy, you have to delve into a thing called the kinetic molecular theory. The kinetic molecular theory attempts to describe the behavior of matter on the molecular level. As opposed to what we call the empirical level or intuitive level. Example would be the gas laws or the kinetic concentration issues. Nothing is said in those or required in solving problems in those issues based on what is the molecular or atomic level doing. Now, we know pressure intuitively is an effect of the molecules bouncing around, but that doesn't come into play. The collision issues don't come into play when you're solving Boyle's law or any of the other Charles law, Gay-Lussac laws, or anything. It's an intuitive. You know, if you increase temperature, a gas is going to expand. The volume is going to go up. Okay, it just does. You don't have any explanation as to why it goes up in terms of the molecular level. This is a molecular level or microscopic, so to speak, consideration of the behavior of matter versus a macro, which is the large scale issue. In kinetics so far, we've looked at concentration changes. Okay, we know the concentration changes and the amount of molecule is going down or up for whatever reason, but we didn't indicate on a molecular level why it's going up or down. So now the last section in here, in order to understand the temperature and energy effects, we have to delve into the kinetic molecular theory of what's happening to the particles in a reaction mix and discuss them in terms of that. Well, there are two theories inside the kinetic molecular rate theory, or the kinetic molecular theory of matter, that deal with rate and temperature and energy factors. First one is the collision theory, which deals with molecules bumping into one another. Okay, out comes a product. The other one is what we call transition state theory or complex state theory. To understand both of these, we have to look at some of the statistical behavior of particles, say in a gas, phase reaction in terms of what we know as a Boltzmann distribution. A what? A Boltzmann distribution. Of the gas phase, energy content of the gas phase. I knew I felt like I left out something. Gas phase particles. Now, need to construct another graph. This. Like this. This time, a Boltzmann distribution says you're taking into account the energies of the particles. Now, let me ask you a quick question, and it's kind of an intuitive one. Do you think all of the particles in the gas atmosphere that's in this room have the same energy? No. Some have low energy, some of them have middle, and some of them have higher energy, based on whatever transfers energy. To establish that on a Boltzmann distribution, we say, or a Boltzmann distribution will have on one axis number of events, and in this case, the number of particles. And it's usually represented by a sigma symbol. You can use any kind of thing you want, but it's the number of particles. And on the horizontal axis, energy content. Increasing or decreasing, like that. At a specific temperature, as I specified in the note, we're going to take a temperature arbitrarily chosen, but we'll map the energy content of the particles at T1. And it looks like this. Some of the particles have very, very low energies under the curve. Most of the particles, you see the distribution, are in the middle of the curve. The median region of the curve, the averages area. And very few particles are out here in this region here for a massive collection of particles. There is a line or point on this curve of energy content that we call the activation point. And is characterized at that point by activation energy. Activation energy is the energy needed or must be contained within a group of particles for them to react and proceed to products. Particles with energies less than this particular value do not have enough energy to proceed to products. Energy. Yeah. Wait a minute. for any reaction to proceed to products. Listen to me. Wait, listen to me. For any reaction, wait a second, to proceed to products, 4 events must take place. They will spell the acronym CENT. Okay? Go ahead. I thought you were leading.
No, sir. I was
Okay. I guess it's 2 E's or 1, I don't know. Let's stuff another one in there. These 4 events, spell the word CENT, not to be confused with the rate factors. These are reaction factors. Different from rate factors. Can't see are the rate factors. But CENT are 4 events occurring all at the same time that are identified as required for a reaction set or system to proceed to products. This includes, these are identified as the proper kinetic concentration. So we'll just write concentration here, and out here kinetic concentration. I'll explain them, I'm going to write them all and then we'll go back and explain each one. Effective collisions. This has to do with orientation of the particles that come together and form or bond. They have to come together in a certain orientation in order to connect. If they don't connect. Like that. Next one's kind of an obvious issue. It must include naturally reacting substances. If you put in substances that naturally don't react, you're not going to get anything out of it. Throw in a couple of metals, they're not going to react. But you'll put in a metal and non-metal, then you have a better chance of getting a product. So, requires naturally reacting substances. And it must be at or above that temperature which will give the system, all the parts, so we're done with reaction, energy above the activation energy. I'm just going to put in activation energy. Looking at concentration effects first. What this refers to is you have to have a sufficient concentration of reacting particles, A and B, say, for A to find B. If we take a reaction chamber, say it's like this room or so, and over here we have one particle right here, a blue particle, and they have to hook up one particle's in that corner of the room, one over here, they're moving around trying to find each other, the probability of them finding each other is very, very low. So what is suggested is, in the theory, is that we increase the number of particles sufficiently so that the particles can find one another and have a better chance of reacting. Yeah. And effective kinetic concentration. Which simply means that unless you take that into account, you're not going to react them. Now, one little sidebar here for this, and I think you understand what I'm talking about here. That's not an issue. But one little sidebar, in practical world, the concentration of one of the components typically will be significantly higher than the other, so that you can get complete consumption of the other. For example, if I have A plus B going to AB, and I want to be real sure that everything reacts so that I can get a stoichiometric amount of AB, one of these is going to be put in, A or B, put into a chamber in excess of whatever the other one is. So you might start out with a specified amount of A, but you'll have a large excess of B, which kinetically says everybody's going to find one another and proceed to react. Now, the outcome of this is that once the reactions start taking place, we start losing A and B, or our blue dots and our red dots start decreasing. Okay? So the concentration of reacting particles goes down, and this follows the kinetic trends that we've been talking about, and explains it in terms of the decay process. The reaction rate of a typical process will decrease as a function of time. Because the kinetic concentration is not at a level that would favor the reaction to occur. See, we're losing red and blues, they're turning into products. And so as you go down this trend, the rate begins to decrease because you have fewer and fewer reacting particles. Now, when you get to very low out here, the particles are so far apart, they're still there. A and B, blue and red, are still there. But they can't find each other, and the reaction almost doesn't proceed. But starting with an effective kinetic concentration of high concentration of 1, you're going to get a real good reaction production here. And it will run until, say, X is consumed, which is the limiting reagent. And then the reaction process just stops. Okay? But in course of going from start to some stop, the reaction will actually decrease in rate as a function of time. So that's how we use the kinetic molecular theory to explain a trend on the molecular level. So that's how does rate decrease as a function of time, or why does it decrease as a function of time? Because the kinetic concentration decreases around the reacting components, and so it goes slower. The next factor is the effective collisions. So when particles react, they have to react in a certain orientation in order to have a good chance of bonding. For example, if I were to draw a weird looking diagram like this, and this is particle A, and over here I'm going to have particle B like this. Bring it down a little bit. If they were to bump into one another in this orientation, what we would obtain is a product that would connect, say, like that. And so A and B have now connected to form a product. If the components approach each other like this, or one approaches opposite like that, this produces no reaction. So molecules in the chemical reaction have a very specific orientation that they have to be in order to proceed to products. Okay, and that's the best example I can give you on that. Now, next one is, of course, intuitively self-explanatory. Okay, so naturally reacting components must be in the reaction process. So there's sodium ions plus chloride ions go to sodium chloride. Well, that's good. But if I put in a sodium ion and I don't know, potassium ions, you're going to get a reaction out of that. Like charges repel one another, so it's not likely. And it works over into more complex molecules, but I think you see the point that I'm trying to make. Now, the kinetic molecular theory doesn't predict the particles needed does not predict reactive particles. It just says that they have to naturally react if they're naturally reacting particles. Under certain conditions, they'll react. And finally, temperature at activation energy. We'll cover this again in a little bit. A couple of ways I could approach this. One, if we use what they call a transition state diagram. I call it positional energy, but most people will call it potential energy, or energy content at a specified condition. When you consider reactants going to products as such, and I'm just going to use one of two kinds, and we'll talk about the others in a minute. The reactants may have to start at a given point, and we call that the positional energy content, or the enthalpy, if you will, content of the reactant. So I'm just going to put the reactants are at this energy level, E sub R. If you raise the temperature, you're going to raise the energy content of the particles. And if you continue to increase temperature, it will reach a point at which it will be at or beyond that point called the activation point, or activation energy. This is the activation point. And is referred to as the activation energy point, the amount of energy it has to go to products. So we're having to add a certain amount of energy, we call delta EA, called the activation energy input, to reach that point. And once you get to this point, the reactants will hold together in such a way as to be a very limited life, and then they'll break apart again in the form of products. Some of them roll downhill to the right and wind up at products at a different energy level. The change in energy observed for this is the difference between the energy, the products, and the energy of the reactants, and that's called delta H of the reaction, or heat of reaction. And in Chem 1, maybe you'll cover thermochemistry, but you will see something like N2 gas plus 3H2 gas goes to 2NH3 gas, semicolon, delta H of reaction, standard conditions, is equal to minus 98.5 kilojoules. And so they stick a number on the end. Well, that's what this is, this differential. The reactants start at a specific energy content, delta H of the reactants. And then the products have a certain energy content after the reaction has completed. And the change in energy of the reaction is the energy content of the products minus the energy content of the reactants. Some of you will recognize this as Hess's law. But here's the kinetic molecular theory saying the particles before reaction, before we get to the activation energy, will have a certain amount of energy, and after the activation energy point, they'll have a different energy content. Now this depicts a negative outcome, which is exothermic. Now there is an endothermic in which they have to go over and wind up here for an endothermic, above the starting point. But all reactions have to go through the transition state, all of them. So even the reactions that wind up below exothermic, and something that winds up here in the product side, hypothetically, would be endothermic. And we'll cover that in more detail in a few minutes. Okay. So that leaves us with the mathematical aspect of what do we have to do with this. But the CENT is the four issues that have to come together for a reaction to occur. All right, going back to the Boltzmann diagram for a minute. When I drew out the Boltzmann distribution curve, I limited it to one temperature, T1. And the activation energy, we're going to put right here to emphasize a point of issue. two things you'll want to keep in mind. One, the activation energy is always constant. Okay. Two, on the average, reaction rate doubles for every 10 °C increase in temperature. Now, mathematically, you can take the equations in the book and show this. It gives you a greater, twice the fraction of particles available. But all I'm going to be working with you on in this context is what happens when we raise the temperature. We're starting at T1. But what happens if we raise the temperature 2 times? Well, what happens is the curve now begins to look like this and distort to the right. That's at T2. So you're talking about energy, number of particles, excuse me, against energy content. Increasing. So if I raise the temperature, I'm going to shift some of these particles that were in this region right here are now shifted over here. So you have twice as many particles able to react or having the conditions necessary to react. And if I continue that, what would happen is I keep heating, the particles would, this curve would eventually start doing this. Like that, T3. You keep going until all of the particles are way up here, starting, you put out enough energy for all the particles to have reactive potential. And so your curve kind of sits up here. And you don't have any more particles over here to the left of the activation energy line. This is significant right here in that anything to the right of this vertical red line represents the particles having all of the reacting factors. So all particles have reaction factors. And so when you get past this EA point, which is right here, everybody can go to products. Mathematically, we're not going to get into how this comes about. It'll take us 2 days. But if you understand here, and I'll ask questions on what happens at the activation point and why the outcome, then you'll be fine. And when you get to junior physical chemistry, the professor may shove all the frequency of collision equations in your face, along with some other. We do have one equation that we will work with that describes this, and it's called the Arrhenius equation. The Arrhenius equation is used to calculate the kinetic rate constants at different temperatures. given an initial temperature and rate constant. The derivation of the Arrhenius equation uses the equations of kinetic, collision, frequency, and probability. Arrhenius showed that a typical rate constant is given by A e to the minus delta E over RT. That's the probability, saying, okay, if you have all the appropriate data, you can calculate the activation energy at a specified temperature.
Is that a RT or a KT?
Okay. Somebody have a question? Okay. Long story short, this equation is divided into K1, T1. You'll have a K equal A E to the K1, say, and I know this is not, I'm not being deliberately logical in this, but you'll have a T1, okay, and you'll have K2 equals A E to the minus delta E A over RT2. I'm just showing you that what the equation defines is the rate of any reaction based on its activation energy and its temperature. And you can calculate this if you add these two together, these two equations together, or equate them through these proportionality constants right here, you'll wind up with the Arrhenius equation. That's the Arrhenius equation. Notice that you have two K values and two temperature values in here. Problem number 19 in the practice exam is using the Arrhenius equation. Example of using the Arrhenius equation. I don't know what I did with it. Anyway, I'll write it out for you. Okay, I'll show you. For the formation of 1 mole of nitrosyl chloride at a reaction activation is minus 36 kilojoules. No, that's not the one I want. Sorry, I was wondering why that was there. The rate constant for a first order reaction is given. Assume A goes to products for a given reaction. This has a K1 equal to 1.5 times 10 to the reciprocal second 1 at T1 equals 726 kilojoules. Thank you. K2 is equal to 3.6 times 10 to the minus 2 seconds to the minus 1 at T2 equals 866 Kelvin, like that. Calculate the activation energy. Of reaction. So you're looking for this delta EA right there. Now you're going to have to learn the equation. Derivation is more than what we really need. So if you look at this equation, the only thing we haven't talked about is the R value right here. R is the gas constant in thermodynamic terms, which is 8.314 joules per mole Kelvin. Typically, the activation energy is reported in kilojoules per mole. So this must be converted to kilojoule terms. Divide by 1,000, so 0.008314 kilojoules per mole Kelvin. Substituting this data into the Arrhenius expression, and this is what you'll be given, and you have to know well, I'll give it to you if you need it, but know to express your R value in kilojoules. The only thing you'll need to calculate is the delta E. That's the only thing left in there, and you just grind through the process. Okay, I'll try to set this up and show you. So we have Ln of K2, well, that's 3.6 times 10 to the minus 2 seconds to minus 1 divided by K1, which is 1.5 times 10 to the minus 2 seconds minus 1 to equal delta E activation energy, what we're looking for, over 0.008314 kilojoules per mole Kelvin, like that, times, a little bit neater than this, one over T1, which is 726 Kelvin, minus 1 over T2 Kelvin, which is 866 Kelvin. So you need to solve that expression for the activation energy. Yeah, it's a plug and chug type of problem right here. Now, when you look at this differential down here, you can calculate out the individual number, take difference and plug that in. What I like to use is this expression just for interest. This is when I take these two and find a common denominator, and then rearrange my data to match this. Now I can solve this for delta EA very simply, which is R ln of K2 over K1, right there, divided by this term, well, I'll go ahead, T2 minus T1 over T1 dot T2. Get rid of that. Okay, the denominator will invert and multiply, and you'll have a form R value times ln of K2 over K1, T1 times T2, divided by T2 minus T1. So it's a little easier to punch all that in. That's my opinion. You can work it like this or however, but however you solve it, you're looking for delta A. I mean E, delta E. Okay, so in putting it in this form, delta EA is 0.008314. I'm just going to tell you, it all comes out in kilojoules per mole to save us some time. Ln of K2 is right here over K1, so we'll repeat this, 3.6 times 10 to the minus 2 over 1.5 times 10 to the minus 2. Seconds will drop out. Actually, this will drop out also. You'll have 3.6 over 1.5. The product of the temperatures, T1 is 726, doesn't matter, 726 times 866, right there. All this divided by T2, which is a larger number, minus a smaller number. And everything will come out in kilojoules per mole. And you try it out at home, work through it units if you want to. Trust me, it's correct. Okay? Sure, I got it. T1 times T2. Okay. Well, I should have paused it while I do the calculation. Okay, so what I got after computing all this is the numerator was 4576.2 divided denominator, the differential is 140, and giving us 32.7 kilojoules overall. Now, whether it's endothermic or exothermic is not defined in this. It just says calculate delta E, and okay, is the transition state theory. The transition state theory says that for chemicals to react, they must pass through an activation energy point. Well, make a long story short, typically there are two transition state diagrams. One for an endothermic reaction and one for an exothermic reaction. So I'm going to draw the exothermic first. It's pretty straightforward, and show you how to use this to calculate activation energies. This is reaction progress. It is not anything numerical in the context of the reaction, but the vertical axis here is a positional energy content or potential energy. The reaction, regardless, reactants goes to products, starts with the reactants at a specific energy level called positional energy of the reactants. Well, we'll put that right there and call that E of the reactants. And to make this react, you have to push it over the activation energy point right here, and the molecule of whatever's formed at that point is called the activation complex. Occurs, and it's had a short life. It may violate the octet rule, but it decomposes and produces products. Sometimes it rolls back down to the, if you will, to the reactant side. So your reactant energies are increased until they get to this point, and once they do, they form products. And once the products are formed, they give up energy if the final product energy state or the positional energy is below the reactant energy. And what this does is gives a change in energy to equal or be less than 0 or negative and is defined as an exothermic reaction. Or MIC reaction. Right there. So, as we've shown you earlier, where it levels out over here, this is your delta E of the reaction. You'll see it used as delta H, but we'll talk about that when we get to thermodynamics. If the final position of the products is below the reactants, then this defines the exothermic reaction. Okay? The distance from the energy position of the reactants to the activation complex up here is what we call the forward activation energy, and the distance of the forward reaction going left to right. So this would be the EA forward. From products going up to the activation level, back here, this is EA in reverse. So if you wanted to reverse the reaction and make it go back to products, this is the amount of energy you would have to put into it to make the reaction proceed in the opposite direction. And of course, as we've just identified, then this is the heat of reaction when you take the differential. I'll show you some problems in just a few minutes, how it works. I'm losing my caps on for these things. Okay. That was the example of the exothermic reaction. Now we need a example of an endothermic reaction. I should have put a heading up here, but here it is right here. Okay. So we need to draw another diagram to illustrate that. And in this one is essentially the logic of it is that the products come out at a level above the reactants energy positions. I'm just going to put potential energy like that so I can have a little more room in reaction progress. Well, again, the reactants would have to have a positional energy, whatever goes in, so your reactant side of the equation, and then you raise, using temperature, the activation energy up to the activation energy, the reactants up to the activation energy, and they form the products, form the complex, and then they decompose into products which are at a nu up here. This is energy of the products right here. And again, this is your activation point, or activation energy complex. This is the EA forward, left to right, reactants going to products. And this one would be, this distance right here would be EA reverse. You'd have to push it back, the products back up to the complex to break it apart and make the reactants now. And then the heat of reaction now is this, the delta E of reaction, which is final E products minus E reactants. Those are positional energies. And this gauge comes out greater than 0. And so this represents an endothermic reaction. If you look at problem 18 on the practice exam, you'll see the type of issue you have to deal with on this. Okay. Now, they're going to give you some energy values for the forward reaction, activation energy for reverse reaction, or the energy value for the heat of reaction, and ask you to calculate one of the three. Give you two of the three. So, I'm going to need a diagram at any whatever you do. So I'm trying to keep it at least tolerably neat. Here. And this is, of course, your potential energy content. All right, from the problem. All right, now the way the problem is described, it is an exothermic reaction. I wish I had the blank, so I don't know what I did with the blank. Very straightforward once you see how I do this, okay? It says, for the formation of 1 mole of nitrosyl chloride at a given temperature, delta H equals a minus 36 kilojoules. Okay, the first note in your mind should be that this is exothermic, so you're going to have to draw an exothermic graph, okay? And this will be representing this reaction. The activation energy is 74 kilojoules for the forward reaction. What is the activation energy for the reverse reaction? From the diagram, you know what to do. So if I take the diagram and this data, I know it's exothermic by the data given. So I'm going to, regardless of how I draw it, I'm going to draw one with the product side below, somewhere below the reactant side. See there? You have to have the products less than the reactants. Next thing you want to do is enter values for forward and reverse, or whatever, are the two of the three energy issues in this reaction. Get this one. See, that levels off about here. Okay, so for an exothermic, that's what it looks like. The products are below the reactants. And they give us in here, in the problem, the activation energy for the reaction. Well, that implies a forward reaction if you're working with this. So the forward reaction energy is 74 kilojoules per mole. So I'd have 74 kilojoules per mole. Right there. It's given the heat of reaction to be a minus 36. Okay, the minus 36 comes out of E product position versus E reactant. Products being lower than the E reactants will wind up with a negative number, and that indicates a exothermic reaction. But the heat of reaction, the absolute heat of reaction, is right here, is the distance between here. Even though it's negative, you don't use a negative in your computation. You can put it there, but the delta E reverse in this diagram, now look at it, be logical. What's the distance from here to here in terms of those two numbers? How would you compute? You would add them together. It's just like two distances. And so the reverse is simply 74 plus 36 in kilojoules, 110 kilojoule. You'd have to put it in positive energy, endothermic, to raise your reactants back up to the activation complex. See how that works? You have to know when you read the problem, whether you're endothermic or exothermic, draw the appropriate curve and fill in 2 of the 3 issues in there. They give you, here's 3 terms that you have to know about. The forward activation energy, the reverse activation energy, and heat of reaction. If it's negative, you know you need to draw your graph with a line below the reactants. Well, they didn't give me another one in the practice exam. Hang on. Well, so you can go back and look at it. Problem 1376. Ebbing, 9th edition. That's on page 574 if you have it. Okay, anyway. The reaction is N2O, nitrous oxide, as a gas, goes to nitrogen and oxygen. Gas. Okay, it is an endothermic reaction. How do I know? Delta H of reaction is equal to plus 167 kilojoules, like that. So now, typically the endothermic reactions will not include a sign. It'll just be blank right there. And if you see it as a blank and no positive or negative, your assumption is endothermic reaction. So that immediately tells you that you have to draw an endothermic reaction diagram. And that would put the products at a positional energy above the reactants. Now you need to draw the diagrams because there's a little bit of twist in how you put these together. You have to be observant in this E, potential, reaction, progress. And we say we start right here, and we just go ahead and draw a curve that comes up like that, back down here, and say levels out there. Now since the reactants are here, products are here, we see and immediately that has a positive heat of reaction. So the difference here, that says products, is the delta H of the heat of reaction. Sorry, I'm trying to get ahead of myself. Heat of reaction between here and here. Okay. The activation energies for forward and reverse. Gets the pin on the marker. Is right here to the activation complex. So this is delta H activation, or delta EA for the reverse reaction. Here is delta enthalpy. H and E is the same. For the forward reaction, here to here, like that. So the problem goes on to say the activation energy for the forward reaction is 251 kilojoules. This is 251 kilojoules for the forward reaction. The heat of reaction is given in the problem to be 167 kilojoules. What's the activation energy of the reverse reaction? Well, the sum of those two matches your forward reaction now, see? So when you set this up, you don't just add them together like you did here and here to get that one, because you have to take into account that one of them's not known, the reverse reaction in this case. is not known. But you still have delta H of the reaction plus delta HA for the reverse reaction is equal to the sum of those two equal that distance of the forward reaction, delta H of the forward reaction. And you substitute and solve, and you get the answer you need. Okay, so for the heat of reaction, we're at 167 kilojoules. The reverse reaction is our unknown, is what the problem's asking for, and the forward reaction is given to be 251 kilojoules. So when you draw out these diagrams, be sure you write out who's doing what and then make your substitutions, and those are gimmies problems. They're really easy. And so the delta H reverse is 251 minus 167, and everything comes out in kilojoules. Okay, that's for the reverse reaction right there. So you see how I'm dealing with that?
Would it not be negative? Negative?
No.
Okay, all right.
Think.
Sorry.
If you change that to negative, what are you doing to the distance? You can't add them together to get this number over here under any circumstances.
Right.
Okay, make sense? That's why I'm making an issue out of drawing the diagrams and putting the numbers in, because the data will come to you as an exothermic reaction negative. Endothermic, hey guys, I ain't through feeding you. You ain't gonna get up and leave mama's table, I tell you. It's slight. If it's an exothermic reaction, they'll tell you it's a negative reaction, but when you do the computations, you have to add both parts of a section to get another section. Okay? So that's why I'm asking you diagram. It is an exothermic reaction or an endothermic reaction, but this problem doesn't depend on, that's the wrong context. It depends on the endothermic exothermic knowledge to draw the diagram, but after that, once you have to use the diagram to add or subtract various things to get the answer they're looking for, so to speak.